the integral test, we have a series, summation n goes from 1 to infinity an. This series, this summation or this sum can be approximated by this integral. So in the series, we goes from 1 to infinity. In the definite integral, we go from 1 to positive infinity. F of x dx, they are either both converge or both diverge. So how that works is we have a function. So this is the graph of the function. We need to make sure that this function is positive. What is positive mean? Positive, f is positive, the function is positive, means that the y is positive. That means the curve must be above the x-axis. The curve must be above the x-axis and then continuous from 1 to infinity. We need to make sure that there is no vertical asymptote between 1 and infinity and decreasing for x greater than or equal to 1. So this is important. You need to show that the function is decreasing in order to use this integral test. In most of the problems, usually the positive and the continuous, they are easy to show. But the decreasing, you may need to take the derivative. So you need to take the derivative of the function, and then you need to show that the function is positive when x is greater than or equal to 1. Why? Okay, this function is decreasing, right? So when you do an integral from 1 to infinity, we are looking for the area under the curve from 1 to infinity. So as x goes to infinity, this area, so that is related to the improper integral that you studied in the past. When x goes to infinity, okay, the right hand side goes to infinity, then you have to tell me when x goes to infinity, is this area equals to a real number like 5, 6, 10, 1/2, 3/2, or the area is equals to infinity. Is that equals to a real number or infinity? Then we will have to look at this piece. Okay, but why do we have to let the series equals to the integral? When you study, before you study definite integral, do you still remember that you study how to use a rectangle? You draw rectangle under the curve to approximate the area. So you draw an integral, not integral, you draw a rectangle like this. So this is a point on the curve, and then you draw a rectangle, and then this is a point on the curve, you draw a rectangle. This is a point on the curve, you draw a rectangle, and then you use the base times height to find the area of rectangle, and then you add them up to approximate the area under this curve. So that's why the summation can be approximated by the integral, but you need to show that the function is positive, continuous. Usually these are easy to show. And then regarding the decreasing for x greater than or equal to 1, you either draw a graph like what we are going to do next, or you need to find the derivative, and then you need to show that the slope of the function is decreasing when x is greater than or equal to 1. So I have two examples below. The first one is n over n squared plus 1. The other one, I just changed the n to a 1. They look so similar. Even the graph looks similar. My question is, as x goes to infinity, is the area under the curve equals to a real number or equals to infinity? Why don't we start from the red problem? Okay, let me match to that color, so this red should be good. And then what we are going to do is, okay, first of all, I have the graph of this function, and then based on the graph, and I can tell that the function is positive and continuous. Is positive because the curve is above the x-axis, continuous from 1 to infinity, there is no vertical asymptote. And then decreasing, I can tell that the slope is decreasing by looking at the graph, and then you go from integral from 1 to infinity, and then you do x divided by x squared plus 1 dx. And then this is an improper integral, you must write the limit. Okay, this is part of the presentation. Writing the limit is required from 1 to b, and then you have x over x squared plus 1 dx, and then this is an improper integral. All right, and then to integrate, I'm going to use u-substitution. We will let u equals to x squared plus 1, and then you differentiate both sides. Du is equals to 2x dx, and then isolate the dx on one side, 1 over dx du, that is equals to dx. And then we will do a change of variable. Use my highlighter, do a change of variable. I will replace this dx to here. I will replace that dx to here. And then regarding the upper and lower limit, the b and the 1, they are in terms of u. So I will not touch that at this point. I will just go ahead and then perform the integration. We have integral. The top is x, the bottom is u, right? And then the dx is 1 over 2x du. And then let me highlight this piece as well. So that one, after a change of variable, that's what we have in the integral. So now the integral is in du, not in dx. So since the integral is in du, you cannot have the variable x in the integral anymore. And then we can see that the x will be cancelled. Then you have integral. How about I do a 1 over 2 and then a 1 over u du. What is the integral of 1 over u? The integral of 1 over u is ln. Then that is equals to 1/2 ln absolute value of u. Absolute value is required because ln negative is undefined. However, after I plug in the x back to the u, I have 1/2 ln. Then now you can use parentheses because x squared plus 1 is always positive. So x is back. And then I will mention that x goes from 1 to b. X goes from 1 to b. Or I should put the limit in front. I should put the limit in front. How come I don't mention the upper and lower limit right there? Right there in this integral. Because that is in du. That's why I cannot mention the upper and lower limit until the variable is back to x. Okay, as x goes to infinity, what do we have? We have 1/2 ln. I have infinity plus 1, and then minus 1/2 ln 1 squared plus 1. What is ln infinity? Based on the graph of ln infinity is equals to infinity. So this is an infinity minus 1/2 ln of 2, and then infinity minus a real number. So this is equals to infinity. So what does that mean? That is equals to infinity. So that is equals to infinity. We can go back to this graph and then say the area is equals to infinity. The area is equals to infinity. That means this summation, when you add up infinitely many terms, the sum is equals to infinity. The area is equals to infinity. That means the sum is equals to infinity. Since the sum is equals to infinity, we say that this series diverges by the integral test. Okay, by the integral test. And then in the blue problem, we have a very similar graph. Do you think this one will be a diverge as well? Let's find out. Okay, match that blue. And then I have integral from 1 to infinity. I have 1 over x squared plus 1 dx. Set up my improper integral, limit as b approaches to infinity. Integral from 1 to b, 1 over x squared plus 1 dx. You may think writing the limit is not necessary because you can just plug in the infinity, but I need to tell you that writing the infinity is part of the presentation of your improper integral. And then what is the derivative of that? This one is not a power rule. It's not power rule. It's not a u-substitution. It's not integration by parts as well. That one, this integral is equals to arctangent or inverse tangent. So that is equals to limit as b approaches to infinity. This one is an arctangent. So that is arctangent x such that x goes from 1 to b. And then you will have an arctangent infinity minus arctangent of 1. What is arctangent of infinity? Arctangent of infinity, we need to recall the graph of it. So this one arctangent, if you still remember the graph of arctangent, which is very popular in integration, arctangent has two horizontal asymptotes. When x approaches to infinity, we have one vertical asymptote at pi over 2. When x approaches to negative infinity, we have a horizontal asymptote at negative pi over 2. So this is a pi over 2. And then arctangent of 1 is pi over 4. Pi over 4, because tangent of pi over 4 is equals to 1. So pi over 2 minus pi over 4, you have 2 pi over 4 minus 1, that is equals to pi over 4. So equals to pi over 4, what does that mean? That means this area is equals to pi over 4. So the sum of this series is equals to pi over 4. That is equals to pi over 4. You are adding up infinitely many terms. The sum is equals to pi over 4. The sum is equals to pi over 4. Therefore, the series converges by the integral test. So the series converges by the integral test. There we go. Oh, and then before I continue to the next problem, this is the graph of arctangent. If you don't remember the graph of arctangent, now is the time to do some review. You need to know this graph, because when you do integration, this integral is very popular because the arctangent has two horizontal asymptotes. So we have the blue curve, arctangent, two, did I say vertical asymptote? Horizontal asymptote, one at pi over 2, one at negative pi over 2. Alright, so that is the basic of integral test, and then in the next video, I will introduce more series. I think the next one I should introduce the P series and the harmonic series. Okay, I will meet you all in there.